I'll give you a quick example. So, because some people think that there's no rhyme or reason behind the Moodle grades.
There is no rhyme or reason.
Oh yeah, the Moodle stuff is like, what? I don't know if it includes empties in your average. I think it does. It's like, it's really weird. So I don't put a lot of stock in Moodle grades at all. Okay, so let's just talk about quickly, what's my grade? So say we have, so say tests are, let's say we have some simple grade setup, right? We had test 1, I think was 10%, test 2 was 15, and then test 3 is 20%, right? But let's say we just have one test and it was worth 50% of your grade, and then we have assignments. This is just a pretend setup to make it simpler. Let's make assignments 10% of your grade. Okay. And then the final, let's make it 40%, right? Total has to be 100%. Okay. Say there were 5 assignments. Making them what, 2% each? What you're gonna do then, right, is you're gonna make a list of everything that you've collected, right, all the marks that you've collected. So you've got your test mark. I'll just put a little header, let's call it the item. And then the grade. I do the grade as a percentage, and then the weight. Okay. Let's say I got a solid 80% on my test. Okay. And then I have assignment 1, assignment 2, assignment 3, assignment 4, and assignment 5, and then my final exam. Let's say I got 100% on assignment 1. I forgot about assignment 2. Oops. And then I got 100%. I tried to redeem myself. Let's say I got 80% on assignment 4. And just for simplicity, another 100%. And then I'm nice and steady, but it was a stressful final exam period, so I got 75% on my final exam. How about? Okay. So the weight of each of these, right? If a test is worth 50%, the weight is 0.5, right? The weight of this one would be 0.2 or 0.02, sorry. Right, 2%, 0.02, 0.02, 0.02, 0.02, and 0.40. This has to total 1. Right. And this is how you're gonna figure out, okay, well, what do I need to get on the final to get a certain grade, right? So you can play around with that final exam grade, okay? And then what you do is you just take your 80 times 0.5, right? So then you have 80 times a half. I have 40 going towards my final grade, right? So, and then I have 0.02 and then a crappy 0. It's okay. Right. And then 0.02 and 80 times 0.02. I got, oh, that's not gonna work. It's 100 times 0.02, so 2%. Sorry, guys. Like I said, forgive me. 1.6, right? 80 times 0.02. And then another 2%, right? And then 75 times 0.4, 30. Right? Usually we don't know this total, right? But if you add up all these guys, 40 plus 2 plus 2 plus 1.6 plus 2, and divide it out of 60, that's your grade before the final. So that's how you're going to keep track of your grades, kind of see where you're at. Okay. That's just not this class related, school related knowledge. Okay. All right. And then the total there would be your grade. Woohoo. Okay. Fun. All right, I guess we don't have any review. We tested it, we're moving on. Let's just start chapter 6 right away. Okay. If you did any pre-reading, I know I'm just throwing that out there in case it happened. So chapter 6 is on what we call annuities. So now we're moving towards the back page. So now we're going to be working on the back page of the formula sheet. It looks a mess, right? But just like we have been doing with the formula sheet, we're just going to plug our way through all these formulas, kind of figure out when to use them, what do they do, right? And just talk about how we use all these formulas, and eventually they'll start to make sense. Okay? So annuities are when we have payments coming to us, or we're making payments at regular intervals, right? So before we've had a payment at year 1 and then a payment at year 3, right? And then what do we have to pay at year 5, right? That kind of thing. So, but now we're making regular payments, right? Think loan payments. Well, they're all loan payments, car payments, right? House payments, all that kind of fun stuff. Okay. We'll deal with mortgages on its very own, and that's that very last section that we deal with. Okay. But annuities are just going to be kind of regular payments that we have to factor in as well, right? Which we've kind of hinted at with the PMT button that we've been leaving empty, right? So we can be making regular payments as well. And phew, we can use our calculator for this fun stuff as well, right? So that'll be part of it, just showing you how to use your calculator for annuities as well. I guess we usually turn the lights out. It's just kind of fun to set the mood. Okay. So what we're going to do today is we're going to, because the problem is, so we're going to have a compounding frequency, right? But now with these regular payments, we're also going to have a payment frequency, right? And so what we need to do is we need to get them on the same frequency in order to be able to deal with them. So what we need to start doing is to figure out, okay, well, how can I change the compounding frequency to match the payment frequency? Okay. And so we need to be able to move between different frequencies. And we've seen that before, right? When we looked at a continuously compounded rate versus, I think, an annually compounded rate. We looked at that most recently. But we've done that a couple of times where we've said, even on the test, right? Oh, was there a message? I missed it. If you're there and you sent me a message, I didn't see it. Send it again. Anyways. Right, so we've looked at comparing different rates. Right, on the test you had a couple of times, or I think just one time maybe, where you had changing interest rates for a short answer, and then I asked you what equivalent rate, right, single rate, would do the same thing. Right, so that's where we're going to start, and we're going to develop how do we change the compounding frequency. Okay. So 6.1. Oh, any questions about the test or any questions before we start all this? Fun new stuff? I don't know about you guys, but to me it feels like it's December already. Because we're getting so close to the end. We only have this much left. And mortgages. Okay. No takers, huh? So 6.1 is on effective and equivalent interest rates. So we'll start by talking about the effective rate. Okay? So we've been given things like 4% compounded, let's make life easier, quarterly. Okay? So that we can convert it to an effective rate, okay? And that's the annually compounded rate that would be equivalent to. Okay? So the effective rate is always the annually compounded rate. Okay? So the effective rate which we denote lowercase I, subscript f, EFF. She said, what? I know. And before we even define it, right, you've got two formulas for the effective rate on your formula sheet, and that's at the very top, right? So we'll talk about those, of course. When do each of those apply, right? But it's good to have a look and say, oh, there they are. Come back to those. So the effective rate is the annually compounded rate that produces the same future value as the given nominal rate. I'll put in brackets what I mean by the given nominal rate, right? R% compounded, and then the frequency, right? Be bi-weekly, quarterly, whatever. So what we use, right, if you have a look at your formula sheet, the effective interest rate is going to be 1 plus I to the power of F minus 1. You might have guessed, right, that the other effective rate is the special case because it has the E in there, right? It's the special case where we're going from a continuous compound to an effective rate, right? So that's the only reason that we need, so that little special case, we need a little special formula, right? But in general, if we're just going from 5% compounded bi-weekly, right, we're going to use this formula. It's only if we're going from continuous to the effective rate that we would need the other formula. So pretty rare. So this is kind of our go-to. Okay. So where I is the periodic interest rate, right? Just the same as before. Periodic interest rate. And the only other thing in this formula is F, which we know is the compounding frequency. Oh. Cool. So I'll steal an example here, quick little example, just to get the ball rolling. Oh, look at that, it's really wavy today. Oh. Weep. What is the effective interest rate of an investment which earns 4.8% compounded quarterly? So we've got R is 0.048. The compounding frequency is quarterly, so 4. We want to find the effective interest rate. Right, what annually compounded rate, that's the effective interest rate, is going to be the same as 4.8% compounded quarterly. So we can just use our formula. We have all the components. 1 plus I to the power of F minus 1. We'll have it memorized in no time. Looks familiar. Sort of. 1 plus I, right? I guess I should have calculated I. Let's just throw it in there. I is R over F, 0.048 over 4 to the power of F, which is 4 minus 1. 0.048 divided by 4. I'll just make a quick note of what I did here. I equals R over F, which is 0.048 over 4. Maybe I'll just skip straight to it. It's almost easier. 0.048870933 is what I get. You have to remember to subtract that 1, right? Your rate is always going to be a small number. So what does that mean? We have an effective interest rate of 4.887%. Right? So an annually compounded rate of 4.887 is equivalent to 4.8 compounded quarterly. Okay. So we can just round to 2 decimal places. A rate of 4.89% compounded annually, because that's what we're doing when we're finding that effective rate. Compounded annually will yield the same future value as 4.8% compounded quarterly. Yes. Any questions about that one? Cool. So, like I said, if we have a continuously compounded rate, right, that's a special case where it's not even every minute, it's all the time. It's continuously compounding right? And so for continuous compounds, for the future value, it's just 1 mark on the test, right? But I was just seeing if you could remember stuff that we covered at the very end. Future value is the present value times e to the RT. I was pretty impressed, actually. What do you guys remembered? So anything with e's and natural logs for the r, that's going to have to do with continuous compoundings. Okay. So if we have a continuously compounded rate, the effective rate is the effective interest rate. Oh, my pen isn't catching. Sometimes it gives me like the real world, like pens running out experience. E to the r minus 1. And that's on your formula sheet. Because if it's continuously compounding, we don't have an f, right? We just have the rate and we know it's continuous. So then we apply the special formula. Maybe I'll square in things that are on our formula sheet like I think I was doing before. This is on your formula sheet. And this is on your formula sheet. Only covered 2 so far, but 2 is pretty good in the first half hour. Oof. Okay. So where R is the nominal rate. So funny, I was talking to someone in the other class and she was like, oh yeah, in class, I'm like, slow down, I can't keep up, you're going so fast. And then she said she was watching the videos. And when you're watching the videos, she's like, come on. So it's just kind of funny and interesting. Second time we hear it. It's like, okay, moving on. Okay. So let's see here. For a little example, let's do example 197. Oops. An investment earns 6% continuously compounded interest. What is the effective rate of interest? Okay. So we're given that R is 0.06, and I'll just make a note here that it's continuous. And I want to find the effective interest rate. So then we have this formula, right? The effective interest rate is e to the r minus 1. So then this is going to be e to the power of 0.06 minus 1. Remember, to find e to the power of anything, you have to have the power on your screen first, and then hit the second log button to get that e to the x. And then minus 1, I get 0.0618365547. So that's just a way quicker way to do what we did before, right? We found the future value of a continuously compounded rate, and then we use that to find the annually compounded rate. But this does that exact same thing, right? And so 6.18% compounded annually is the same as 6% compounded continuously. So what do we have here? So therefore, 6.18% compounded annually is the same as 6% compounded continuously. No, you can just leave it as the number. I just want to emphasize what we're talking, because it's pretty new still, but yeah, just the number is fine. Or if you want to show off that you know what the effective rate is, and we love to show off. Oh, by the way, I saw beautiful timelines, so I'm very pleased with you guys. And also there was an unintentional curveball on the test. Where was it? It was where you found the n to be 17.33 repeating. Which one was that? 5. 4B? Yeah, I know it's the marks throwing us off. The n didn't work out. That was a sloppy mistake on my part. But, so if you use 17.3 repeating as your n, that's good, that's fine. But if you took it one step further and said, well, we can't actually have 0.3 of a compounding, I have to round to 18, I did give out a bonus mark. What? I know. So I caught that during the test, but I was also pretty curious to see who kind of had that going on. It was good. Okay. But a lot of people just went with the 17.33 as if it was normal. Okay, that's good. That's good. Okay. So effective interest rates, they're kind of I don't know, a special case, right? Because we're only going from some compounding rate to, or compounding frequency to an annually compounded, right, frequency. Now we want to be able to move from quarterly to bi-weekly, right? So we don't always just want to move to annual compounds, right? And so that's when we're going to get into equivalent interest rates. So equivalent interest rates. Oh, equivalent. Interest rates. Technically, two equivalent rates are two rates that have the same effective rate. Right? If you map them back to the same effective rate, they're equivalent. Right? We kind of skipped that step. That would be really annoying and tedious to have to find the effective rate of this one and then the effective rate of this one. Make sure that they're the same, right? But it'll help us develop a new formula. So two interest rates that have the same effective rate. That definition isn't as helpful as the other one, right? But like I said, we're going to use it to develop this new formula. Okay. So what I'm saying is that the effective rate of the first has to be the same as the effective rate of the second to be equivalent. Right. Oops. Just make a note here, to be equivalent. And so I know the effective interest rate has the formula 1 plus I to the power of F. Now this is for rate number 1, right? So I'm just going to put little subscripts on the I and the F, and then minus 1. And then the same thing for the effective rate 2, regardless of what your I and your F are, right? We can denote them by I2 and F2. So 1 plus I2, F2 minus 1. On our formula sheet, right, we've got this formula in terms of I2, right? So let's just solve for I2. We could have solved for I1, it doesn't matter. But let's solve for I2. So it becomes a matter of moving things over, right? Trying to shake out that I2 and have it on its own. And so keeping I2 steady, we first have to add 1 to both sides, right? So then we have 1 plus I1 to the power of F1 is 1 plus I2 to the power of F2. Right, once I add 1 to both sides, the ones disappear. So now, to get rid of that F2, I have to take the F2th root of both sides. Ugh. Well, let's do it and see what happens. The F2th root of 1 plus I1 to the power of F1 is 1 plus I2. Right, now that we've taken the F2th root, we just have the 1 plus I2. Nice. Remember that trick we used where we rewrite the root as a power with a fraction? Right. So this would be the same as 1 plus I1 to the power of F1 to the power of 1 over F2. Right? Which is 1 plus I2. Because this is the trick that you use to take whatever root you want, right? Not always taking the square root. Right? So if you want to take the 20th root, for example, then you take the value inside to the power of 1 over 20. 1 over F2 is the F2th root of what's inside. Okay. So now, right, that's why we worked with those exponent rules and then eventually our log rules, right, to be able to do stuff like this, no problem. Right. Now I can merge these, right? Just multiply across, and that's how I get the F1 over F2 in the power. Nice. What? I know. 1 plus I1 to the power of F1 over F2 is 1 plus I2. Now that I've simplified that left-hand side as far as I can go, I can subtract 1 and just have I2. So 1 plus I1 to the power of F1 over F2. See how those subscripts are really important, right? Which frequency came from where? Minus 1 is I2, right? Or as it's written on your formula sheet, I2, bless you, is 1 plus I1 to the power of F1 over F2 minus 1. And that's the one on your formula sheet. So what's this doing? This takes, so let's say we're compounding quarterly, right? We've got 4% compounding quarterly, but our payments are being made monthly, right? That's where we're headed with this. We have to match our payment frequency. So that means instead of compounding quarterly, right, F1 would be 4, we want to move towards compounding monthly to match our payments, right? So our F2 would be 12. And so this formula gives us the new periodic interest rate for compounding monthly in that example. Okay. So we use this, right, when we want to go from compounding at a frequency of F1 to compounding at a frequency of F2. Okay. So we use I2 is 1 plus I subscript 1 to the power of F1 over F2 minus 1 when we want to change the compounding frequency. When we want to change the compounding frequency from F1 to F2. So then I2 will be the new periodic interest rate, right, at a frequency of F2. So I2 will be the periodic interest rate at the new compounding frequency. So before, right, we started with simple interest and then we could just convert the R to a decimal and go ahead and use that. Then we moved into compound interest where, okay, so now I have to take that R and convert it to I, the periodic interest rate, in order to do our calculations. Now in annuities, you have to check your compounding frequency versus your payment frequency. If they're not the same, you'll first have to convert to I2 before you can do any calculations. And then you'll use I2 in your calculations as your I. Okay? So it's just another step that we keep adding on, right? I think it's a good idea in general, and I'll do it, just identify the payment frequency and the compounding frequency right off the bat, right? And then I always convert the periodic interest rate right away, and then I don't forget to do it, because they have to match. But we're not quite there yet. So let's see a little example, example 198. Oops. Oops. Now we can read that. An investment earns 5% interest per year, compounded semi-annually. How much interest should alternative investments, which are compounded quarterly, pay, right? So what equivalent interest rate would compound quarterly? So we've got R1 is 0.05 and F1, right? It's compounded semi-annually, so the frequency is 2. we want to find R2. And we're told that F2, we need to compound quarterly. Just like before, in order to find R, we first have to find I, right? Find that periodic interest rate. And then we can use the same I equals R over F to find R. Okay. So, all right, let's just jot down our formula, I guess. Just trying to think if we need anything. Just looking at this formula here, we can find I1 separately if we want to, right? Let's do that. I1 is R over F, which is 0.05 over 2. 0.025. You can do it inside the formula if you want to, or you can do it separately. Doesn't matter to me. So now we can say I2 is 1 plus I1 to the power of F1 over F2, all minus 1. The periodic interest rate for the first one, right? The first rate is 0.025. So 1 plus 0.025. And here's where we have to keep track of our F1s and our F2s. So our initial frequency was 2, and we're moving to a frequency of 4. F1 over F2 minus 1. So this one. So I get 1.025 to the power of 2 over 4 minus 1. I guess I didn't need to write that one down. But here, 2 over 4 is kind of easy. But in general, on your calculator, right, you would have 1.025 and then the y to the x button, and then brackets 2 divided by 4 and brackets. And then equals to the power of 2 divided by 4. Even if it is something as simple as 2 over. Pardon? Yeah, so in this case, it's easy enough to just do it in our heads. But if we have kind of weirder stuff like going from weekly to, I don't know, daily, that's going to get weird, right? So we don't do that in our heads. So for me, I just always follow the same procedure, but you can absolutely just do 2 over 4 in your head and just do that. But I get no, that can't be right. What did I do here? 1.025, oops. 1.025 to the power of 2 over 4. There we go. Has to be 1. 1.012422837. So make sure that that's what you're getting. So 1.012422837 minus 1. I would probably end up storing that if I was doing a problem, right? But this becomes 0.012422837. This is the periodic interest rate if we're compounding quarterly, right? So now find R2. I is still R over F. Right. Or in this case, I2 is R over F2. So we've got 0.012422837 is R over, what do we say, 4? So then R must be times 4. 0.049691346. Therefore, a rate of 4.9, let's say 7% compounded quarterly is equivalent to what do we say? 5% compounded semi-annually. It's equivalent to 5% compounded semi-annually. Sometimes I hyphenate, sometimes it's one word. Pretty sure the jury's out. Semi-annually. Twice a year. Nice. So as we expect, right, they're similar, right? But I'm compounding more frequently now, so it's gonna need a lower rate than compounding semi-annually. Right? Nice. We have the same special case for the continuous compounds, right, where we don't have a frequency, so we need to be able to deal with that. But remember, all these continuous things, they're pretty rare, right? It would be maybe a short answer on the test, right? Those continuous compounds. But for continuous compound, or for continuously compounded interest, we can convert to a different compounding frequency. By, and even if you just had to guess which one it is on here, you would probably use I2 equals R to the E to the power of R over F, all minus 2 or minus 1. Yikes, can't talk anymore. Shame, that's why I'm here, to talk. So I2 is E to the power of R over F2 minus 1. So whenever you have that E in there, it's going to be linked to continuous compoundings. So this is on your formula sheet. Where F2, right, is the desired compounding frequency of I2. Where F2 is the desired compounding frequency of I2. We can also use this R formula. Okay. R is the nominal rate, right? And then F1 times the log of 1 plus I1. Okay. This is going to convert some rate to a continuously compounded rate. Okay. We can also convert a given rate with compounding frequency F1. Notice that the ones are always the ones where we start with, and then the twos are where we want to end up. All right, just keep that in mind. So we can also convert a given rate with compounding frequency F1 to a continuously compounded rate. And we use R equals F1 times the log of 1 plus I1. And that's on your formula sheet as well. So when it has that log, the natural log, right, you're going usually to continuous compounding. Okay. I think the textbook just uses R is F times the log of 1 plus I. I don't like that one because I like the one that's on your formula sheet, right? F subscript 1, I subscript 1, saying, hey, this is where we're coming from, and then we're going to a rate, and that rate must be continuously compounded, right? So I don't want to, that's from the textbook. But because it doesn't have those subscripts, I don't think that it's as clear of a formula. Okay. So on your formula sheet, you have that one. But if you see it used in the textbook, then they're just the same. Let's do an example looking at this. Example 202. An investment earns 5% interest per year compounded quarterly. What is the equivalent continuously compounded rate? So we know that we have R1 is 0.05. F1 is quarterly, so 4. If we know R and we know F, we can find I1, which is R over F, which is 0.05 over 4, 0.0125. Yes. So we want to find R, right, where we're continuous compounding continuously. We've got 3 if we include the effective rate, right? But we have 2 formulas that match our continuous compoundings, right? One is for I2. That's giving us a compounding frequency. We want to move from a compounding frequency to continuous, right? So that means we have to solve for R. R is F1 times the log of 1 plus I1. F1, we're moving from a frequency of 4 times the log of 1 plus 0.0125. Take the log of that times 4. I have a rate of 0.049690008. Okay, or did something happen? Yeah, got it sorted. So I took 1.0125 and then I took the log of it, right, the ln. Hit the ln button. Once you have the 1.0125 on your screen, you hit the ln button and then times 4 and then equals.
So ln equals and then multiply.
Sure. It shouldn't matter. Good. So what does this mean? It means that a rate of 4.97% compounded continuously is equivalent to 5% compounded quarterly. Therefore, a rate of 4.97% compounded continuously is equivalent to 5% compounded quarterly. Nice. Let's do example 203 as well. Look at how tiny it is. Oh yeah, we can handle that. What monthly compounded rate is equivalent to 9.5% compounded continuously? Right, so now you want to move from a continuous compound to a monthly compound. So we've got R is 0.095 continuous. And we want to find R, or R2, I guess, or F2, right? What monthly compounded rate? So we're moving, we want to go to a monthly compound, so frequency of 12. So, because we've got that continuous compound, we have to use a special case, right? So I2 is e to the r over F2 minus 1. Which means we have e to the power of 0.095 divided by our desired frequency of 12 minus 1. So we have 0.095 divided by 12. Okay. So we've got e to the power of 0.007916 repeating minus 1. To take e to the power of that, right, you have to go, so you have to have that 0.007916 on your screen, and then second log button gets you the e to the power of x. and then equals. So then I get 1.00794886 minus 1. So that gets us 0.00794886. Right. Now we can use I equals R over F to find R. Or I2 equals R over F, oops, 2. I2 is 0.00794886, so you probably want to keep that on your screen, right? Times R over our desired frequency of 12. Times that by 12, we get 0.095377036. Therefore, a rate of 9.54% compounded monthly is equivalent to, what was it? 9.5% compounded continuously. Notice with these equivalent rates and even the effective rates, the moves aren't that big, right? But in terms of money, this is going to make a big difference if you have enough money. Right? It's all relative, right? And so we want to be careful with our rounding, right? Not rounding until the very end, because we are talking money after all, right? And then just as a check, when you're finding these equivalent rates, they should be very similar, right? 9.54 is very similar to 9.5, right? Ooh. So, any questions about that one? No? Then we're ready for annuities. 6.2 is simply titled Annuities. So an annuity in general is just a series of equal payments, right, for some amount of time at regular intervals. Right? So any sort of loan repayment, we've usually got it set up with a bank or whatever. Okay, I'm going to pay you $500 every month for this long. Right? And so that would be considered an annuity. So an annuity is a series of equal payments at regular intervals. We've seen baby scenarios, right? Equal payment amounts. That's when you have to put in X there and then solve for X, right? But they weren't necessarily at regular intervals, right? Sometimes they were, but often they weren't, right? I make a payment at 2 years and then I make another payment at 5 years. I need to have $700 in 6 years, right? That kind of thing. Now we're making regular payments, regular equal payments. So we're going to talk about things like the payment interval, which is exactly as it sounds. the amount of time between payments, right? The amount of time between payments. And then we've got periodic payments, right? Which is going to be the amount of these equal payments that we're making, right? Because each period we're making some payment amount, right? Or maybe getting a payment amount. That sounds better, right? We're getting some equal payment amount, right? And then to total some grand total. So we'll talk about the periodic payment. And that's just the amount of the equal payments in the annuity. This we're going to be denoting it by, so it's denoted by PMT, right? We've seen that PMT button. We've ignored it until now. But that's the amount of each of these equal payments. And then we'll be throwing things like the term around. The term is just the duration of the payments, right? So common car loans are, I don't know, 5 years, 4 years, 6 years, 8 years, whatever, right? And so that would be the term, the duration of the payment or of the payments. What's nice about all these is we kind of, yeah, those are all kind of, I don't know, self-descriptive. Payment interval, periodic payment, the term. Here's a twist. For annuities, N isn't going to be the number of compoundings anymore. N is going to be the number of payments. Did I say that right? Yeah, I did. So I tell you with the straight face, and then I have to check if it's right. It is. I knew it. I'll put a little star here. So when discussing annuities, N, right? N will now denote the number of payments as I kind of hinted at before, right? We've got some compounding frequency and a payment frequency, right? How often are we making these payments? And because we want, we can't change the payment frequency, that is what it is, right? But we just learned the tools to adjust our compounding frequency to match this payment frequency. That's why for annuities, now N is going to be the number of payments because we can adjust the number of compoundings, right, to match the number of payments. Okay. So I guess technically it'll be the number of compoundings as well. No, don't worry. Okay. There's a lot of formulas for annuities. And the reason for that is that there's different types of annuities. Okay. So let's make a little, I tried to think of a better way to make this kind of tree, but it splits off into different directions. If you can think of a better way, tell me. Okay. So the first type of annuity is you can have an ordinary annuity or an annuity due. So an ordinary annuity is where the payments are made at the end of each payment period. It's late last night when I read these notes. Okay, at the end of the payment period. And that's what we've kind of been assuming, right? An annuity due is where the payments are being made at the beginning of the payment period, which is only going to change things slightly, right? But because you're making payments a little bit earlier than you would have at the end, right? That amount should be earning interest and taking into account that interest that gets made while it sits there for a month, let's say. Right? If you're making the payment at the beginning of the month versus the end of the month. Right? So let's do our first two branches. Just straightens out my lines for me, which is nice. So we can have an ordinary annuity. Oops. And that's where we're going to start. Where payments are at the end of each payment period. Or we can have an annuity due. Where payments, give myself some more room here. Payments are at the beginning of the payment period, right? They're due at the beginning. So payments are at the beginning of each payment period. So we'll develop first how to deal with ordinary annuities, and then we've just got a slight twist to an annuity due, right? The hard part is recognizing it in the question, right? Payments are made at the beginning of the month, for example. Then you have an annuity due. The idea stays the same, but the formulas change a little bit, right? If you look at your formula sheet on the right-hand side, you've got some subscript due, right? So we can do everything with annuities due that we can with ordinary annuities. Right. So that's why it's not that big of a stretch to go from ordinary annuities to annuities due. Right. Just the question changes a little bit. We have to switch up our formulas. They just change slightly. But the idea stays the same. And then, regardless, we can also have I'll just start another annuity branch because this goes for ordinary annuities, but I don't want to have to write it all out twice, right? And it goes for annuities due. So annuities can either be simple. Okay. Simple annuities are where we're going to start, where our payment frequency and our compounding frequency are the same, right? Which simplifies things a little bit, as we've seen, because if they don't, right, then we have to adjust our compounding frequency to match the payment frequency. And that's when we have a general annuity. So general, so simple annuity and a general annuity. A simple annuity is where the payment period coincides with the compounding period. Payment period coincides, I'll just put in some more brackets there, that it's the same as the compounding period. Or frequency if you want. Whereas a general annuity, right, that's going to be more likely on a test. We start with a simple annuity so we don't have to deal with adjusting the interest rate. But we already know how to do it, so we could just skip straight to general annuities if we wanted to, right? That's where the payment and compounding periods are different. Just make a note here. This is when we need to find I2, right? Just like we did at the beginning of class. Right. Find your new periodic interest rate. Okay. So we can have simple ordinary annuities. We can have simple annuities due. We can have general ordinary annuities. We can have general annuities due. Right? So we can have a combination of these. That's why I wrote out another branch, because I didn't want to have to duplicate them over each of them. Okay. So we'll just start working our way through all of these. We'll start with the most basic, right, where we talk about a simple annuity, simple ordinary annuities, or ordinary simple annuities. I don't think it matters how we say it. Okay. As long as we say all of it. So we'll start with ordinary simple annuities. Let's start by having a peek at your formula sheet. Right. And just looking at the left-hand side for now, right? We're doing a simple annuity or an ordinary annuity, so we'll ignore the annuities due for now. Right, so just the left-hand side. And it gives us two formulas for the future value and the present value, right? So they're not in the same formula anymore, right? So which one we use is going to depend on which one we want to know or do know. Right? So we'll look at examples of that. And then, same idea, depending on which, if we know the future value or the present value, we'll have two different formulas for finding n, right? It just depends on the information that we have, right? And then, yeah, we'll talk about perpetuities, but we'll leave those. They're really fun. It's where you get payments in perpetuity forever. How do you deal with that? Anyways, we'll leave that little tidbit. Okay? But that's just a quick run through of a good chunk of these formulas, right? The problem, right, why we have so many formulas is because we have these two formulas for the future value and one for the present value. Right? So, in the case of n payments, remember n is now the number of payments. Right? For compounding, just simple, like easy, I shouldn't say simple compound interest, just kind of basic compound interest, n is still the number of compoundings, but for annuities, now n is the number of payments. Right? So in the case of n payments, we find the future value. We find the future value by the future value formula is the PMT, which is that payment amount that you're making at each payment period, right? PMT times 1 plus I to the power of n minus 1 over I. That's on your formula sheet. As always, we kind of start by introducing all these formulas and then we apply them. Or we can find the present value by the present value is the payment amount. It's going to have a similar setup, right? But things change in these big brackets where we have 1 minus 1 plus I to the negative n over I. So your timelines now are going to be oh so important, right? Because whether you know the future value or your present value, or want to know the future value or want to know the present value, that's going to dictate which formula to use. So depending on if we want to find the future value or the present value, we will need to pick the appropriate formula. Need to pick the appropriate formula. So let's have a look at example 204. Martha contributes $10,000 each year to her RRSP. That's another likely scenario, right, where we're contributing money, equal payment amounts. Usually the bank sets it up, right? They just take the same amount every month. At a rate of interest of 7% per year, how much will she have after 25 years, right? So we're making payments per year. We don't actually want to be calculating every single future value for these $10,000 for 25 years. That sounds terrible, doesn't it? Doesn't it? So we'll start with a timeline. For these annuities timelines, I want to see the starting tick and then 2 ticks on the front and then 2 ticks at the end at least, right? That's all you need, okay? And then we can just put dots in between to tell us that, hey, everything stays the same for all these 25 years or 20 whatever years in between. Okay? So what I mean is, right, we start today with our payments, okay? And then she's making payments every year. And interest is compounded every year as well. So that's our first check. For now, we don't have to worry about it, right? Because we're talking about simple annuities where the payment frequency and the compounding frequency, they are the same, right? Later on, that's going to be something that we have to pay attention to, right? How often am I making payments? Is it the same as how often I'm compounding? If not, I have to adjust my compounding. But for now, we ignore it. So then 1 year goes by, 2 years go by, and then time passes, and then I'm at 24 years, and then finally 25 years. Right, so as a little note here, I want to see 3 ticks in the beginning and 2 ticks, so at least 2 ticks at the end. Right, time ticks. And then dot, dot, dot in the middle. So we can put our amounts, right? So every year she puts in 10,000. So 10,000 here, 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 and finally at the 25th year, the last 10,000. If it said the payments, so she's going to make these payments starting today, right, and make them at the beginning of each year, then we would have an annuity due, right, which would mean we'd have a different formula to use, slightly different. Okay. Instead of drawing, you know, this, so future value 1, we'd have 24 future values we'd have to calculate, right? That gets nasty. So instead of drawing that, we do this. We do our beautiful curly brackets, or just a square bracket if you want. I think it's pretty fun to do the curly brackets, so why not? Yeah. So all of these are going to get funneled to one future value. Right. And that's what we're going to use for our annuities, right? When we've got all these payments, we just show a couple, right, to give the idea of the lay of the land, and then we funnel them all into this future value. So N is the number of payments, right? I'm making 25 payments. So I'll put that on my arrow. We're told that the rate is 0.07. And the frequency is per year. So I is R over F, which is 0.07 over 1, which is 0.07. Oh, because it's compounded per year. So now I can use the future value formula. The future value is the payment amount. So the amount of each of these payments, right, is 10,000 times. You'd have to use the future value formula because we don't know the present value is 0, right? She started with 0. That doesn't do anything for us, right? Or if you're still kind of wrapping your head around present value, future value, right? If you think of it this way, the present value is always on the left and the future value is always on the right, right? So the arrow is going to whichever one you're calculating. That's just a little note. Back to our calculation here, we've got 1 plus I to the power of n minus 1 over I our payment amount is 10,000 times 1 plus 0.07 to the power of n, which is 25 payments, minus 1 over 0.07. We got to deal with our brackets inside our brackets. So 1.07 to the power of 25. Just showing a lot of work for now, but it might be easier for you guys if you just kind of go to the end, I guess. Going to be easier than stopping and writing down your work. I know that. 5.42743264 minus 1 over 0.07. Is that what you guys got? 1.07 to the power of 25? Oh, minus 1 divided by 0.07. So we get 10,000 times 63.249037772 times 10,000. She's going to have a whopping $632,490.38. That's great. She did have to cough up $10,000 every year, but still pretty good. Right? Because how much did she pay out of pocket? So it's pretty good. Right? Nice. Well, she paid $250,000. Inspiring. All right. Cool. Let's do one more example, and then we can get out of here. How about that? 210. Oh, this is the funny one. Okay, I'm glad this came up today. Well, it's not that funny. The names are funny. Hank borrowed money from Tank. Hank agreed to make yearly payments of $2,500 for 12 years. Right. So he's making yearly payments. If Tank charges interest of 13% compounded annually, right? So yearly again, so they're matching. It's a lot of money. Yeah, yeah. I guess Tank's the hard ass. Yeah. Hard to keep those guys straight. So if Tank charges an interest rate of 13% compounded annually, right? So we just do a little check. Okay, we're making payments annually, we're compounding annually. Great, we don't have to deal with that. What was the amount of the loan? So the amount of the loan is going to be the present value, right? How much did he borrow initially, and then he's going to be paying it off, right, with these payments. So let's draw our timeline here. So he borrows some money today, and then he's going to make yearly payments. So 1 year, 2 years, and then ... for a total of 12 years, and throw in 11 years as well. And then he's going to make payments of $2,500, $2,500, $2,500, and $2,500. Right. These are all paying off some original amount of the loan. Right. So these are all going to funnel back to some present value. The future value of this should be 0, right? He should have paid everything on. And the number of payments, right? He's making yearly payments for 12 years. So we've got 12 payments. We're told that R is 0.13, yikes. And the frequency is 1, compounded annually. Right, so then we know that I is R over F, but because F is just 1, it's 0.13. I'll just, sure, 1. So then we want to find our present value. So it's going to be set up the same way, right? So if you're making payments and you're saving some amount, you're going to be calculating a future value. If you're paying off a loan, you're going to be calculating a present value, right? How much was the loan? So then your present value is the PMT, so the amount of each of these payments, times 1 minus 1 plus I to the negative n over I. So this becomes, the payments were $2,500 times 1 minus 1 plus 0.13 to the negative 12 over 0.13. I'm going to do everything in the big brackets in one foul swoop. About that, 1.13 to the power of 12 negative, I get 0.23. 1 minus that guy divided by 0.13 equals, I get 2,500 times 5.9176470017. So you want to make sure that you're getting that same value, those exact same values. Times 2,500 to finish it off. So he borrowed $14,794.12. How much did he have to pay? 12 times 2,500. But had to pay each 30,000. Maybe I did it wrong. Seems high, doesn't it? 12 times 2,500. That tank. Yikes. What a deal. 12 years, $30,000 later. Hope that 14 grand was worth it. Anyways, we'll keep working on that. But till then, have a great long weekend, you guys. And if you didn't get your test back, I think everyone has theirs. So it's great.